All right, everybody, welcome to Dam Safety Technical Training. Today's seminar is on overtopping protection and will be given by Owner Tastan. Um, Owner is a recent employee with CDM Smith. Owner, you've been with us for a month, but Owner has a very nice resume. He's working out of our Charlotte office. He is a geotechnical and structural engineer, has over 9 years of experience in consulting on national and international nuclear power plants, dams, water and wastewater conveyance and treatment systems. So he's got a lot of nice experience. He has academic expertise in soil liquefaction, and his professional experience includes field investigation, design, laboratory and in situ testing and numerical modeling. His focus is on dams and dam safety analyses, including seepage, slope stability, piping uplift, and deformation analysis, as well as seismic safety assessments. So let's welcome Dr. Tastan for overtopping protection.
Thank you, Pat. Good afternoon, everybody. So, in our last presentation, Steve and Tommy talked about spillway types and designs, stilling basins, and this presentation today is a follow-up to that presentation because sometimes spillway capacity may not be enough, especially if the design flow has changed or you change the category on a dam and you may need that extra discharge capacity. So in those situations, you may have to do overtopping protection. So today, we broke this presentation into three main parts. The first one, we're going to talk about the hydraulic design aspects. The second one, we're going to talk about some of the design considerations for the selection of the overtopping protection method. And then what are the commonly used methods available out there for overtopping protection. So here's a list of references that were used while preparing this presentation, so it will be available to you if you need to go take a look at these references. So overtopping protection, the design of it requires multidisciplinary approach. You need to have hydraulic engineers, geologists, geotech engineers, and sometimes structural engineers too. So this part is related to the hydraulic aspect of it. And as you can see, this slide shows the moment of overtopping with the flow over the embankment. And you can see that the flow is broken down into subcritical and supercritical flow regions. The part on the left is increasing velocity and decreasing depth. On the right, you have the supercritical flow, increasing velocity and decreasing depth again. And down below the slope, you go down towards the toe, and it's again supercritical flow, and it turns into subcritical flow. And at the toe of the dam, where you have the hydraulic jump, is also a zone that is critical during the overtopping protection design. The discharge equation is an equation that you've seen in the previous presentation. So some of the other important equations to use in the design. The velocity and the shear stress or tractive stress are the two more important equations that need to be made available for the design. And the terms used in these equations are given on the right. So in this slide, you can see that the region that is overtopped is broken into three zones. Zone 1 is a subcritical zone, low energy, and erodes only when highly erodible materials exist. Zone 2 is a transition zone to a supercritical, same energy as Zone 1, but involves higher shear or tractive stresses over a limited length. And Zone 3 is supercritical zone, steep energy slope, and high erosion potential. What's not shown here is the toe of the dam, and that's also a critical area and highly erodible zone. So some of the design considerations. So everything you're going to see on this particular slide and on the following slide are the things that we need to address when we're designing overtopping protection. the ones underlined are kind of the more important ones. So we need to start with the discharge capacity calculation and how much extra flow we need over the dam. The flow velocity and shear stress calculations are the first things we need to do. And what's also important are the surface discontinuities, where those zones are more likely to erode. So when you're doing the design, of course, we need to pay attention to the economics part or the aesthetics part, and also the maintenance requirements as well, and all the other things that are listed here. So the common overtopping protection methods. The first one is vegetation, and as you can see, so this is the first one is just the plain grass. The second one, you have a turf reinforcement underneath the grass, and in this particular case, it is from testing where the material underneath eroded, so you can see the turf reinforcement actually displaced downwards. Here you can also see the turf reinforcement over which they're laying down soil. You can also have synthetic turf. This is not natural grass, and it's placed over a layer of geomembranes. You can see here, and this is a subgrade material, a geomembrane over it, and then you have a geotextile over the membrane, and finally the turf material with an infill. So you can see two different types of geomembrane, and we'll talk about it when we come to that type. Another one is roller compacted concrete. So this is a derivative of concrete, and it can be placed in stair steps, formed or unformed fashions. You can see the stair step version here. The next one is soil cement. This is not as commonly used, but it's a mixture of soil and cement, and it could be used again in a stair step or a flat plate type arrangements. Articulated concrete blocks, you can see again here on this slide, gabions and riprap. So this is a table that is provided for your reference, and it provides different types of protection systems and the velocity and the shear stress ranges over which these methods are applicable. You can see that the grass has the lowest velocity, 9 feet per second. If you go over this velocity, you're going to have to use one of these protection mechanisms. So here's a list of analyses that need to be done as part of the overtopping protection design. Like we mentioned, discharge capacity, erosion potential, seepage and uplift. You're going to see that these are particularly necessary for impermeable types of protection mechanisms. Slope stability, and of course foundation stability, settlement, and filter compatibility. So the first method, vegetative and turf reinforcement. Vegetative cover, turf reinforcement mats, synthetic turf revetments, these three types. For large flows, only vegetation may not fully protect against failure, but it may just give you enough time for evacuation, and it requires, of course, good maintenance to provide the service. Here is again a bunch of different vegetations and velocity ranges here. They're all less than 9. Do you remember the 9 that I showed in the previous slide? Turf reinforcement. This is placed under the cover, vegetation cover here, and it could be 2-dimensional or 3-dimensional, and filled with topsoil. Here's an example, overtopping you see on. Another reference for you, where you have a limiting velocity on y-axis and the time hours on the x-axis, and the different types of protection methods, plain grass, and go all the way up to open mats, and the limiting velocity increases. So for the turf reinforcement, we have different types. And you can see the limiting shear stress and the velocity increases if you go to a different type from top to bottom. This is a common one. And then you go all the way bottom, you have the high performance turf reinforcement mat, HPTRM. These are included in this slide so you can easily compare other different types of protection methods to the TRMs. So if you remember from the previous slide, I say the first one was the more the first generation landlocked TRMs. Their lifetime is provided as 10 years by the manufacturer. So if you go to the HPTRMs, their lifetime goes up to 50 years, and they can withstand higher velocities and shear stresses. So here are the steps in selection of the TRM method. By the way, these are at the bottom of the slides. You're going to see that references are included. So if you are curious about any of these particular methods, you can go to their websites and find out brochures or technical product sheets. Just example. So let's talk about the design part of this turf reinforcement. You can see it laid down on a slope, and a couple of important parts of the design. You can see here the initial trench and the terminal trench that is used to anchor down the TRM. And along this direction, you have the longitudinal trench as well. So here you can see the overlaps, and you can also see the pins and earth percussion anchors that are placed to keep it in place. Here's a detail of a trench. You see the pins. You see the longitudinal edge trench. This is in the direction of the flow. And you can also see that, well, maybe not so much in this slide, but they're placed more frequent in the overlap zones. So the initial trench detail at the bottom, you can see the TRM comes down, goes into the trench, comes around, goes back up the slope. There's about 2 feet minimum overlap, and an anchor is placed right here at this location where there is the overlap, and also at the bottom of the trench right here. And this is at least, again, 2 feet deep. So here's the detail for the pin and earth percussion anchors. The earth percussion anchor is something you see here. We're going to show more details about this in the next slide. So you have this piece right here that kind of ties the anchor in place. And then you can see a simple pin detail here. And they are placed in checkerboard arrangements, as you can see. And they're placed more frequent, especially pins along the overlap zones. Here's how the earth percussion anchor is installed. You just vibrate it down or hammer it down, and then remove the rod, turn it around, load lock it, and clip the cable, and it's installed. Again, some details as to how the longitudinal trench and the terminal trench are installed. In the longitudinal trench on the sides, it doesn't go around the trench completely. It just stays here at the bottom and anchored down. And the terminal trench, you go up the slope, go inside the trench, go around, come back towards the slope, and again there's an overlap, and an anchor is placed here, and an anchor is placed right there. Detail of an overlap with a series of anchors and pins placed, and also the anchor detail you can see here. So, after TRMs, let's talk a little bit about the synthetic turf. In the earlier slides, I mentioned that the geomembrane here can be of 2 different types. It could protrude into the subgrade material, or it could be a simple flat geomembrane. Of course, this one can resist higher velocities and shear stresses. On the right, the manufacturer of the synthetic turf provider carried out some tests at the CSU facility, Colorado State University. This is where I went to school for my PhD. You can see the wave generator here and the slope over which they installed the material. You can see the geomembrane placed here. On top of it, the synthetic turf, infill material, and the installation is complete. They let the wave generator provide water, and you can see in these couple slides, these couple pictures, and check for erosion. Here's a plot that shows the performance out of that test. Test duration versus cumulative overtopping volume, and the hydroturf material that they tested on that slide that I showed you is shown here. And it, according to this test result, it outperforms the HP TRM and the TRM with dormant Bermuda on clay. But the ACB, which we're going to talk about in a second, performed better on that particular case. ACB is articulated concrete block. So the next type is roller compacted concrete. RCC is a mix of crushed rock, natural sand, gravel, and cement. And sometimes you can see fly ash being added into this mixture as well. And it's a zero slump concrete. And it can be carried and hauled in vehicles or conveyors. And you can spread it with an earth moving equipment, and you can compact it with a vibratory roller. And it's generally cheaper than concrete. So in a way, it kind of looks like a soil material, but it is very high strength and erosion resistant. And here are some examples. It's a stair-step RCC construction here with training walls on both sides. High up view of the same dam. And you can see it here, the RCC and the spillway. This is a flat plate RCC example. So some key points to address with RCC. Since RCC is a strong material and also relatively impermeable relative to the shell material here, there are uplift considerations that we need to pay attention to. And seepage pattern changes when you place this RCC right here. That's why, as you can see here, circled with red, we have to place a drain against the uplift and a filter material right under the RCC here. And there's also two walls here. You can see the cutoff wall here and a cutoff wall there. So this cutoff wall is also important to make sure that we protect against erosion around the foundation material here in this zone where there's going to be a hydraulic jump. Just like any other concrete material, RCC is prone to heat of hydration and associated cracking. It requires continuous monitoring for mixing and placement, and the placement, of course, is also time dependent, being a product of cement. You can see a detail of a stair step here, and here it's a sloped, unformed, and there could be a form here, and the space in between this zone and the form can be filled with conventional concrete and grout-enriched RCC or compacted RCC. But the compacted RCC in this tiny area is difficult to do, so it's a more common thing to do grout-enriched RCC. On the right, you can see more details and the form work and the different layers of RCC. This detail is from Saluda Dam. It's not necessarily overprotection method, but it's an RCC dam. This picture doesn't have the highest quality, but it's good enough to show you that the unformed version of the RCC here on the right, and the stair-step version of it here on the bottom left. Some pictures about the construction. You can see the RCC material is being spread just like an earth material, and then a grout placed here next to the form. They're vibrating, I think this is conventional concrete here. They're vibrating the concrete, and then they're compacting the RCC with the vibratory roller drums and carrying out a density test after the placement. Examples of poor construction and better construction: on the left you see the poor and the better on the right, and you can see the formwork around here as well. Depending on the project and the requirements of the project, sometimes you may choose to leave the RCC as it is or choose to place soil over it. So if the overtopping protection mechanism is expected to be used, say, every 50 years or every 100 years, and if you place soil around it, it will be eroded only every 50 years, so it may not be a problem. But if overtopping protection is required every so often, then it may not make sense to place the soil material over it. But for environmental reasons or aesthetic reasons, sometimes you may choose to place the soil and the vegetation. This is from a Hungary mother dam. I'm not going to go through these particular slides, but they are there for your reference. They outline the steps involved in the RCC mix design. But the bottom line on those slides is to get the right compressive strength, design water content, and the density, which will provide you the appropriate strength and durability for the design. Aggregate size, water-cement ratio, compaction curve, choosing the right water content, and then looking at the age part and water content part as a variable and design the RCC mix. So the next one is soil cement. Soil cement protection involves mixed and compacted mixture of cement, soil, and I want to underline this word. It could be in situ, soil and water. It could be constructed in a flat plate or stepped face construction, just like you see in the RCC there. And here's an example of it, how it looks like. Flat plate and a stair step, and you can see it's placed up and down on the flat plate, compacted up and down. So the differences between RCC and soil cement mixtures. RCC is generally stronger, and soil cement uses on-site soil, which is an advantage. Both involve mixed design. Both need to be designed for seepage, uplift, and drainage. And I just want to underline that soil cement is less permeable than soil alone. And both require continuous monitoring and placement. FEMA makes the following remarks on soil cement if it is to be used for overtopping protection: that it does lack quality bonding between lifts, and significant separation can occur between lifts, and it requires thicker sections compared to RCC. You can have more cracking, and it has less erosion resistance. That is why soil cement is not very often used for overtopping protection, but it is used for more upstream protection purposes. The next one is an articulated concrete block, ACBs. On the right, you can see here different types of arrangement or different types of blocks. And these things typically can fail due to loss of contact with the subgrade material underneath it. They can have vegetation filling, and they need to be anchored at high stress zones. And we place a geotextile underneath these ACBs. And this is important. They can be placed under dry or wet underwater conditions. And we need to make sure that there is a competent foundation material underneath the ACBs. And the velocity is as high as 45 feet per second. This is not a typical common velocity. It's just to say that they can go as high as 45 feet per second. There are pictures of some of these ACBs. You can see the vegetation over here, vegetation and filling in the ACB. Here's another one. You cannot claim that there's an ACB there, but Steve promised me that there's ACB underneath it. The grass grew over it by time. So this plot shows comparison of ACB against riprap. So the revetment thickness for the riprap here on the y-axis, and you can see different types of ACB blocks. 4.75 inch here, 6 inches, 8.5, 4.75, but with granular material underneath, and it's tapered. It's not flat top. And in comparison, what would be equivalent to that is 12-inch riprap here, 24, 48, 64. So at this point in time, the riprap becomes uneconomical, unfeasible, and ACB becomes a more feasible option to go. As I mentioned earlier, here's the reference for you to go dig more information on it. Different types of ACB blocks, flat top, geotextile right underneath, but there is no granular material underneath the ACB and over the geotextile here. It is able to carry less flow and shear stress. And in this case, you have a tapered top, geotextile, and granular material in between. This can sustain higher velocities and shear stresses. A design chart here for an open cell block, closed cell block, different types of ACBs, and you take a look at the shear stress requirement from your design right here on this column, and you can choose the right ACB type. Steps involved in the construction. We clear the slope, and then we lay down the geotextile, and then we bring the ACBs and place them over the slope, and then we anchor it down. So here's a free body diagram that shows the forces acting on the ACB block. So this is just showing it for an individual block here. The drag force, uplift force, and the weight components associated. And there could be additional forces here associated with the this block trying to go over the next block during the flow. The critical parts about the design. Make sure we have enough, we have the right contact with the subgrade material, and make sure we provide initial, terminal, and longitudinal anchor trenches, just like in the TRM that we discussed earlier. And include earth percussion or helical anchors at critical locations or discontinuities, and provide geotextile underneath the ACB, and if necessary, provide a granular filter layer. So for the design is based on a moment-based method of an individual block. In this method, you disregard the tie between the ACB blocks, where you actually have a tie in between those blocks. And the design is based on a safety factor that you calculate based on slope parameters, flow parameters, and the forces involved in the free body diagram that you saw earlier. And here are some other terms that you're going to need in that safety factor calculation. It's an involved process, multiple equations, but I provided all the terms here for you, and you can just put it in a spreadsheet and design it. But those 2-3 slides were the safety factor involved with the design. But you also need to know what is the required safety factor. So to calculate the required safety factor, you start with a base safety factor, and for overtopping spillway, it's 1.8 to 2, and then you determine a factor based on consequence of failure, low, medium, high, extreme loss of life, and you choose an appropriate factor here. And then choose another factor that accounts for the uncertainty in the hydrologic or hydraulic modeling. And then you calculate the composite required safety factor and compare that against the one that you calculated earlier. And if you don't get enough capacity, then you have to change your ACB type. The other detail about ACBs, as I mentioned earlier, is the anchor. So for the anchoring, you need to provide at least 2 rows. You can see here, 1-to-2 slope is shown here, or it could be 1-to-1. You can you see here. This is for the transverse anchor trench, or longitudinal, and this is the downstream trench where you have a riprap material here, concrete fill here, over the 2 rows of ACBs. Like I said earlier, you need to provide your textile under the ACBs, and in some cases you may need to provide the filter layer. If you remember some of the ACB types, they had a tapered top. On those ones, you have to provide the granular material underneath it, and at least 4 inches of filter material, and then provide the topsoil and seed it, or sod it. Gabions. I'm sure you've seen these around the highways and mostly used in construction projects, but you can use it here as well. And you can provide protection up to discharge capacity of 40 feet cubed per second per feet under velocities of up to 30 feet per second. Here's a basket case. You can see the baskets are placed, the stones are placed on top, and the mesh is laid on top. This is a flat face type application. Here's a step down application, and they both have the anchor down here, downstream anchor. You also need to place a bedding layer underneath for both cases. The last one is a riprap. This is more robust than turf protection, but requires careful design detailing and construction QA/QC. We need to remember that for non-uniform flow, standard flow equations do not apply for design. And for this, research has shown that it's better to have uniform size and avoid gap-graded materials. What's gap-graded mean here is this condition. The other factor is that the riprap can be grouted. You can here see the spillway application where riprap is placed and grouted, and it serves as energy dissipation. You can see these rocks here placed, and it's a grouted layer that is more erosion resistant. For the design, provided equations for your reference, discharge capacity and the D50 to be used for the riprap. You can see a design chart here, the discharge capacity, slope, and different D50s. So that's all that I have. Any questions? After which, we have our own questions for gifts, right? Questions? I guess it depends on the case you have, the hazard associated with it, discharge capacity you require for that specific case. In terms of price, of course, the earlier ones, vegetations and TRMs, would be the cheaper ones. But you may sometimes need a more robust system like RCC or ACBs, more hard armor type, depending on how much discharge you need, how much shear stress is involved. Um, 1 psi is 7 kilopascal. That helps. Approximately. That's how I usually correlate in my mind. Yeah. That's a more like a hydraulic question here, Steve and Pat. It depends on how much energy dissipation you may want to have, right? The stair step versus flat. I forgot to mention that part. How frequent? That's a good point for asking a question then. What was one of the important things about the RCC design that we need to pay attention? I didn't do a good job. Yeah, uplift protection. Provide the drains. Observe the good things. the hydraulic aspect, what are the two most important parameters that we need to calculate? Right method. Actually, there are three that come to mind directly when you consider this. How much discharge do you need? That will give you another one. You're talking about Lake Johnson Dam. I think we had shown the picture of that, if I'm not mistaken. Not this one. It's this one. That's in Riley, yeah.